All right, so yeah, this is joint work with Misha, who's here as well. So I want to start by pointing out an interesting phenomenon that many others have noticed in the past as well, which is that in deep learning, you see that models that are trained to near zero loss on noisy data can still generalize relatively well. And the question is, why doesn't this noise lead to horrible overfitting? And so recently, people have done theoretical work to show that instead you see this benign overfitting, and you can show this holds for linear regression, random features regression, and kernel methods. And kind of the intuition is that you learn these sort of spiky plus smooth models, and these spikes that come from overfitting have small volume and high dimension, which leads to not hurting the test error so much. And what these works show is that benign overfitting happens in special situations, and they require specific conditions on the algorithm and the data distribution. But one thing that seems to always be true is that you need to be heavily overparameterized. And so a question is this somehow fundamental to this phenomenon? And so what we show in this work is that, at least for linear predictors that are fitting the training data below the noise level, they must be significantly overparameterized to generalize well. And this is true essentially no matter what the algorithm or the data distribution is. And so to make these notions more precise, we'll consider the squared loss, so the squared training loss and the squared test loss. And in this setting, the optimal predictor for the test loss is just given by the conditional mean. And so to evaluate the predictor, a natural quantity to consider is the excess loss. So it's test loss compared with the optimal loss. And the models we'll consider are these linear feature models, which are linear predictors on top of a feature map. And so, for example, we can just consider, as in vanilla linear regression, just the identity function, or more generally, we could consider something like a random feature map. And so given a feature map, we can define the feature matrix from the data, and we'll say that the feature map is non-degenerate if this feature matrix has full rank almost surely. And an important definition is this notion of tau overfitting. So we'll say that an algorithm A is tau overfitting if, given a data set, it outputs a linear predictor such that its training loss is at most tau times sigma squared. And so here we can sort of think of tau as the loss normalized by the noise level. And if tau is less than 1, then that's what we mean by fitting below the noise level. And just to note that a lot of the theoretical work on benign overfitting only considers interpolating predictors like the minimum norm solution, which has tau equal to 0. But in practice, tau will always be greater than 0 because we'll early stop and never really fit to exactly 0 loss. And so now our main result is that if the feature map is non-degenerate and there's noise in the problem, that is, the conditional variance is at least sigma squared, then the expected excess loss is at most this quantity sigma squared n over p times 1 minus square root tau quantity squared. So just to reiterate, on the left-hand side, this is the expected excess loss. And then on the right-hand side, we have the number of data points, the number of parameters, and then this parameter tau. And what this result is saying is that if we're fitting below the noise level, that is if tau is less than 1, then we need overparameterization beyond just enough to fit the data in order to have low expected loss. And just to note, we're restricting to tau being at most 1, because if tau is greater than 1, then the optimal predictor is admissible, and it achieves excess loss equal to 0 and training loss sigma squared. So now to kind of unpack some consequences, if we want some rate on the excess loss, that's something like n to the minus alpha, then what this bound is saying is that either two things happen. Either we're fitting very close to the noise level, that is like tau is almost 1, or we must be in this so-called modern regime where we're heavily overparameterized. So the previous bound was non-asymptotic and independent of the distribution, but we can have a sharper analysis by making some distributional assumptions and looking at asymptotics. In particular, we'll look at Gaussian-like data. So the setting here is that the data is Gaussian, and we're in this asymptotic limit with n and p going to infinity at some ratio gamma, and that the true model is linear with some additive noise. And here we can define a special quantity, the minimum excess loss, which is exactly the minimum excess loss of a linear predictor subject to this training loss constraint. And then in the asymptotic regime, we can define an analogous asymptotic quantity, this epsilon star of tau gamma. And we can show that under this Gaussian assumption, we essentially have that from the Marchenko-Pastur law that our universal bound becomes tight when we're heavily overparameterized. So this minimum error becomes exactly the bound that we had earlier, sigma squared n over p times 1 minus root tau squared. And in this figure, I've kind of plotted for various values of tau. In the solid line, the exact value of this minimum error, and then in the dashed line, the lower bound. And you can see that once p over n is large, the bound becomes tight. So yeah, as I just mentioned, the general bound becomes tight in this overparameterized regime, but it can be improved when we're closer to the interpolation point, and in particular, exactly at the interpolation point when p equals n, the minimum error scales something like 1 over tau. But just to raise a point, even though this peak is very interesting mathematically in this like sort of double descent phenomenon, in practice, observing a peak is very fragile. And part of the reason is that the peak behavior is very sensitive to regularization. So if we increase tau just a little bit from 0, then in fact, instead of having 1 over 0 blowing up, we get something finite. Whereas when we're in the tail, where p is much bigger than n, there's much less sensitivity to this parameter tau, since 1 minus root tau squared doesn't vary as much. And just to put some numbers, like in practice, we can imagine tau being something like 0.5, and in that case, this 1 minus root tau squared factor is 0.7, and so this is essentially almost the same as having tau equals 0. And so an interesting consequence is that even if we just fit slightly below the noise level, we still have the same consequences as if we were interpolating exactly with tau equals 0. Yeah, and this figure just kind of illustrates some of the quantities I was talking about, where really it's this second tail in the descent, which is interesting since that's where we can hope to get good performance. Yeah, and just to finish off and summarize, what we showed is that there's this universal lower bound on the excess loss of linear predictors, which fit noisy data. And we showed that this bound actually becomes tight in this asymptotic setting with Gaussian data when we're in this tail of the double descent with over-parameterized models. Yeah. Thanks.
Thank you. Do we have any questions? In particular, any trainees have questions?
Yeah.
I'm just wondering why your bound depend on the interpolation. Isn't it that there should be a better estimator that will not depend on this like interpolation peak?
Sorry, I didn't quite understand.
Because you're saying that like you can predict with a bound the interpolation regime when n is equal to p. Mm-hmm. So it means that the estimator that you're considering is not the right one. So isn't it that your bound should not depend on that? Or it's just because you're limiting yourself to this space of estimators?
Right. Yeah. So the interpolation regime. Yeah, I'm restricting to estimators where p equals n, and what the bound is showing is that like if p is equal to n, then no matter what you do, you're going to have very bad error. So this is just another way of saying that you don't want to estimate with p equal to n. You want p to be much bigger than n.
Or that there is another estimator that will be better. I mean, you don't know that.
When p equals n, there's like no estimator that's good. That's the point.
No, because you consider only this set of functions. So there might be another one that will be better.
When p equals n, like,
yeah.
or so the claim is just that if p equals n, like any estimator will have at least that error. Like it doesn't. It's independent of what. This is like an algorithm independent lower bound. Like if you fit below the noise level, you will like incur a penalty, no matter what you do. Like however you got to that solution, that
I understand. It's just that for me it's weird that you have this. I mean, I think it depends on the space of the function that you consider, on the set of estimators that you consider.
Yeah, I mean, the only assumption is just that it's like this linear predictor, and yeah, that's about it, and that the features are full rank. Yeah.
Okay, thank you.
Yeah. So and of course, yeah. There needs to be noise. That's what I mean. Like, if you fit noise, then you'll have this bound.
So, but do you think that if you will take a non-linear set of estimator, then you might have no interpolation, or is it?
I think maybe under like some more assumptions that even nonlinear predictors would have some penalty for this sort of thing, but yeah, because basically the problem is that you'll have very bad conditioning if your data and number of parameters is the same, and if you are poorly conditioned and you fit noise, then bad things happen. I think that's
okay. Thank you. Thank you very much.
Next question.
Thanks, Nikhil. So does this linear feature model include neural networks as well, where P is like the last layer, the width of the last layer, and then you have some dense layer at the end?
Yeah, so it'll hold, I think, if you consider a random neural network at initialization. But I think after training, you may not have this like non-degenerate assumption necessarily. Like the feature map might become low rank and not full rank. So
sorry, what is that assumption? I guess I'm just not remembering it.
Yeah, so yeah, this is the assumption that so capital Phi is like the feature matrix, and what I mean by non-degenerate is that this feature matrix has full rank. So I think a trained neural network, what I'm saying is just that like the feature matrix might not exactly have a full rank, but I think basically the same result will hold. Just instead of P, you like replace by the rank of the features. And so that should still hold for like neural nets.
So this is this rank is the like discrete rank. So it seems like kind of weird, like if you just train a neural network somehow.
Yeah, that's true. Yeah. So yeah, I guess maybe even if you just train a neural network, this should still be true.
Yeah.
Yeah.
And I guess my follow-up now that you bring this up is, what does this assumption mean actually?
Sorry, what is?
I am struggling to interpret this assumption. Like, just is there like a quick one sentence like what this non-degeneracy
this
is?
non-degenerate assumption?
Yeah. Yep.
Yeah, I mean it's just saying that like if I look at my data points, you're not going to have like them lying in a lower dimensional subspace than the number of data points you have. Like if I have 3 random data points, they're not going to lie in a 2-dimensional subspace. Yeah.
Gotcha. Thanks.